Hi everyone, and welcome to the webinar Attributes of a High Performance Low Latency Database, and the database in this case is ScyllaDB. Let me quickly introduce myself. I'm Zach Leviatan, VP Product at ScyllaDB. Before working for Scylla, I work mostly in the telecom domain as a developer, system engineer, and product manager. Spent a few years at Oracle, and in the last 7 years, I'm deep into a NoSQL database and high performance system. So what we're going to cover today is a brief review of ScyllaDB, then 20 years of hardware evolution, 5 minutes, a brief history of system and database in the last 20 years, especially from the hardware perspective. Then I'm going to explain how Scylla matched this new design perfectly, show some result of the Scylla design, and then a summary and the Q&A at the end. So about ScyllaDB, ScyllaDB is a company that exists for 7 years. Scylla project is a NoSQL database focused on high performance, as we're going to demonstrate in a few minutes. Scylla have 2 API that you can work with. One of them is compatible with Apache Cassandra. The second is compatible with Amazon DynamoDB. When I say compatible in this case, I'm talking about the binary level of the protocol, or in Amazon case, the HTTP protocol. So you can use any driver that work with either database to work with Scylla. Scylla have its own driver and its own fork that give you an additional performance boost, but that's out of scope for this session. As I mentioned, Scylla focus on performance and consistent low latency, and come in 3 main variants. So one is the open source. You can go to GitHub, download the C++ source code, compile it if you like this kind of things, or just download the binary, use AMI, Docker, etc. We also have a closed source project named Scylla Enterprise, which is based on the open source, but do include some extra features, mostly around security, but also around performance, compaction strategy, and other feature. But most of what I'm going to mention in this talk apply to both open source and enterprise and Scylla Cloud. And Scylla Cloud, last but not least, is a database as a service version of Scylla Enterprise, meaning that we are managing the cluster for you on either AWS or GCP, monitoring 24/7, upgrades, and everything that come with managing a database. We have offices and developers really around the world, and we are hiring. So let's get started. Before I jump into the high performance of the design part, I want to quickly map Scylla into the NoSQL database, because as some of you know, there are many, probably thousands of NoSQL databases, each with different properties. So you can map the NoSQL database or database in general in a few ways. I'm going to use 2 methods to map Scylla to its location. In this presentation, one is using the CAP theorem, which it's basically, for those of you who are not familiar with it, it's basically a trade-in between, or a trade-off, sorry, between availability and consistency. On this category, Scylla, like Cassandra, DynamoDB, and other database fall into the more available category. Scylla is use what is called eventual consistency or tunable consistency, which allow you to set the level of consistency that you want to have on your database. And as a trade-off, it's relax some of the guarantees about consistency. So you don't, in case of a failure, either networks or node, you won't always get the latest value that you insert. On most cases for sure, but in some cases you won't. And in return, you get much better high availability. Other way to categorize a NoSQL database is using the data model. So I placed here a few popular NoSQL database based on the data model. The most basic data model is key value, which is you have like a search key and then a value. The value, by the way, can be much more than value. It can be an array, a small data structure, and if you stretch it, it can be a full document. That's where a document store step in. The most popular is MongoDB, but there are many other, and I'm sure people are familiar with it. The third category, which Scylla fit into, is what is called wide column store. You can think of a wide column store as a key value, meaning that you have one key you can search by. Once you found a partition with the key, you can search by the clustering key or ordering key, as it's called in DynamoDB, and then you get the values. And again, the values can be pretty complex. And there are more types of NoSQL database. There is graph database, there is a time series database, there is geolocation database, and more and more and more. So this is just like a sample of the huge amount of NoSQL database out there. And specifically for Scylla, we are aiming, and I'm biased, but I think we achieve it, to be the most performant and best designed wide column store database out there. How is distributed NoSQL database built? And this is not just for Scylla, it's for the entire category. So the database, of course, cannot fit into one server on one node, because by now we are talking about many terabytes, even petabytes of data. And we're talking about high availability across region, AWS region or GCP region, or just different locations. So the database is distributed. The data is partitioned between the nodes. In the Scylla case, there is a function called partitioner that partitions data between the node. Usually every information element is replicated at least 3 times across each data center. So in case you have a failure, even 2 failures, you are not losing all your data. And by the way, this was recently tested in an actual fire. For one of our customers, we have actual fire in his data center, and lucky for him, he was smart enough to set up a cross data center application with Scylla, so his application continued to serve customer. And as I mentioned, you can use Scylla as a cross data center high availability. So some of the information can be replicated to both data centers, some of the information, and it's up to you, can be replicated only in one data center. And of course, you can have much more than 2 data centers. You can have 3, 4, 5, how many that you want. Everything is active. There is no like a master in the data center or master at all. All the nodes on the Scylla architecture, and that's true, by the way, for Apache Cassandra, for example, all the nodes are symmetric. So that was a quick brief to Scylla, and what I want to cover in the next few minutes is the hardware revolution in the last 20 years, and then I'm going to loop it back to Scylla and see how Scylla design was affected by this evolution. So if you look at most application out there, and in this case it's Cassandra, but it's certainly not limited to Cassandra or even to databases, the way that this kind of a system work is it have thread pool, and by the way, usually it's more than one pool, it's multiple pools that work with clients. All of these threads are have a shared memory, data structure in memory that they are managing. So as you know, if you want to access the same data structure from multiple threads, you have to implement some kind of solution, usually locks, that locks the memory between them, and that's go for other resources that the computer have, that the server have. In many cases, at least on Cassandra case, all of these threads, or some of them, are using mmap to map memory into files, and this eventually go to disk. So this architecture is good, and it was very useful 20 years ago, but something changed. And what changed? Let me skip to that. So a few things. First of all, the price of a memory or a RAM was dropped significantly. You can see this is a graph from 1970. It's probably started before, and for sure will continue after. So memory become cheaper and cheaper and cheaper by 1,000-fold, and probably more in the future. That's one huge change. A second change is the number of transistor per CPU. I'm sure you're all familiar with the Moore law of doubling the CPU every 18 months. But if you look carefully of this chart, you will see something interesting. While the number of transistors do continue to increase, the frequency of a single core is actually flat across the last 15 years or so. And the reason for that is simple. There is a limit to the frequency you can push into the CPU. And at some point, the heat that created will be just too much and you have a fire. So there is a physical limit to the frequency. And as a result, the performances of single thread application started to plateau as well. So of course, the vendors are well aware of that, and they have a solution, increasing the number of cores on a server. So if for the older crowd out there like me, if you remember that 4 core in the machine was considered to be huge, today we have 4 cores in each laptop and even more, and production server can go up to 96, 128, and more core, and for sure it will increase further. That was a huge change in the architecture of the hardware that we are using today. And by the way, that's applied for VM on AWS as well. You can these days hire a huge VM with many cores. But the software was not as fast to change. So the software was still in the similar architecture like it was 20 years ago. As a result of that, you can go in different directions. So one direction is to actually run multiple instances of the server of your application on the same hardware, either yourself or using Docker or using other mechanism. That makes sense and actually work, but you are paying a cost for this extra layer of complexity and the extra layer of management. Another solution, and this is a solution we implemented with Scylla, is try to match the design to this new architecture. So this is like a quick summary of what I covered earlier about the changes in hardware. Another change that some people are not aware of is what is called non-uniform memory access, or NUMA. That's actually a result of having more and more logical core on the same CPU or the same board, that the memory that this core have access to is not completely symmetric. Rather, you have parts of the memory which are closer to one CPU or one core, and other part of the memory which are closer to another core. And again, this change at most, or I don't know, many of the application written are simply ignored. And in Scylla, we had the benefit of implementing or designing a database from scratch once this new hardware architecture become more popular. So we had the benefit of designing the database for this architecture and for the assumption that you have many cores on the same server. So if you had the benefit of implementing an application from scratch these days, assuming that you know what you know now about modern day architecture, what such architecture will be. So ideally, it will have no locks, no shared memory that create congestion, removing all or most of the coordination, removing most of the context switch, and do not copy memory from a place to a place. And that's basically what we did, and that's what we're going to cover in the next segment. So with Scylla, we basically had the chance to design a database from scratch with performance in mind. So when you design an application, you can focus on many things. The focus that we chose initially was to take an existing API like the Apache Cassandra API first, and then the DynamoDB API, and try to implement this API, but with a completely a new engine, focus on performance and on latency. And what is the difference between these two I will cover next. So the first and most important decision, or the core decision, is share nothing, block nothing architecture. So if in the left you see a thread on a typical application, they are competing with each other on every resource, mainly memory. So every time 2 threads need to access the same resource, they need to implement a lock. And if you profile such application, you will find that waiting on locks is actually a huge part of what this application is doing. And that's applied for the kernel as well. So the kernel also compete for the same resources and need to implement locks. The nice puppies on the right is the approach that Scylla took of dedicating one thread per core. Each thread is pinned to a core. It's never switch. We don't have context switch at all. Each of them have its own pile of food, if you will, or water. So it doesn't have to fight with another puppy on the same resource. And the same goes for thread. Once you allow the thread to execute all of the tasks that you have without waiting on a lock, everything works much faster. But of course, the implementation is completely different. So we are not using thread pool, and you need to recreate the entire architecture. And that was the basic principle that started the C-Star and later Scylla. So the approach that we took is actually not new. The approach of sharding or partitioning, it's a well-known concept that is actually used in distributed database for quite some time, and I talked about it earlier. The basic idea here is to take your huge amount of data, run some function that will partition it to nodes or to partitions, and then keep each of the partition on a different node. So that's a well-known architecture, but at least on Cassandra and other databases, this principle only used to split the data between servers or between nodes. We took it a step further and also split the data on the machine itself to cores. So each core run its own thread or process. It's not really a process, but it's run on its own thread. And actually, you can think about it as a mini database running on each core. This is a great simplification, but it's because it's not actually a mini database. Why it's not a mini database or even a mini node? Because it doesn't have to use networking to communicate with other cores. It can use other method. There is no chance that one of the core will fail and the other is not. So it's not as complex as a real distributed system, but we did use the same principle of partition the data between the core. And so on something like a 24 core machine, you will see that you have a Scylla thread per core. And as a result, and I will demonstrate it later, the performance of this platform actually scale linearly with the number of core, which is something which is very hard to do in a traditional database or application that was built without these assumptions. So introducing C-Star. C-Star is a C++ framework that was created just for that, for running process per cores. It was created initially about 6 years ago, and since then helped to implement different applications. Some of them is written here, like the Scylla database that we are focused on here, but there are more applications from Red Hat, Redpanda, and other. By the way, the results here on the right are basically from the period that Scylla or C-Star was introduced, and a little bit outdated now. The principle of C-Star I mentioned earlier is about running a thread per core, and not relying on the operating system to do rescheduling. Each core implement its own scheduler for many tasks, direct IO, self-managed cache, and more. I will touch on some of these points later. And by the way, it's completely open source. So if you are considering building your own high-performance platform, maybe you should consider C-Star. So on the left here, we see the traditional tasks that I showed earlier with all the puppy fighting with each other. And on the right, we have the Scylla architecture. And this, I don't know if you can see it from the diagram, but this task scheduler, core database, and queues are implemented per core. So each core have its own thread running this task. Each thread have its own scheduler that schedule task one after the other in a completely asynchronous way. In the case that this core do need to synchronize with other cores, and it does happen, of course, it doesn't use shared memory, rather use an implementation of queues or messaging. So each core will send like a message to another core. Of course, it's very efficient, and this core will execute and send the message back if you need to. Everything make sure all the tasks are completely asynchronic. So this entire architecture is based on the fact that everything is asynchronic. If this thread is blocked on any resource whatsoever, this entire core, physical core, is halt because it cannot. There is no other thread to take its place. So everything is based on the fact that everything is asynchronic, including network, including storage, synchronization with other cores, etc. And another thing that this architecture allows us is to be cache efficient and NUMA friendly. Because each of the core have its own segment of the memory, we can make sure that the memory we allocate for each core is physically close to the core. As I mentioned, in NUMA, not all memory parts are in the same distance or latency from each core. Unified cache, that's another advantage of Scylla. So in application like Cassandra and other, they are heavily relying on the page cache. And that have some limitation. It does work, but have some limitation. And the limitation is mainly on performance. The page cache is using page fault in the kernel, which introduce latency. So latency might not be as bad if you have multiple thread, but on Scylla we cannot, since we are focusing on very low latency, we cannot allow that. So we're not using Linux page cache, rather we implemented our own cache. And we defined what is saved there and what is not. SSTable is a format that both Cassandra and Scylla keep their file on disk, but we're not going to focus on that today. So I mentioned earlier that the cores actually do not share resources and do not have to synchronize on resources. This is not completely accurate because they do share some resources, and one of them is the disk. So storage, of course, is a super important part of a database implementation. At least a persistent database heavily use the disk, and the disk performance is a huge part of what the database does. So there is a very challenging question how to maximize the disk utilization. So first in Scylla, we took a design decision to focus on SSDs because we are focusing on latest hardware. Scylla will work with other storage type, but not as efficient. And the question that we have, or the question that Scylla have, if you will, is how much concurrency you can put on the disk to make it efficient. So as you know, the disk itself or the storage itself implements some kind of queue, and you have a limited concurrency. So even if you have a very efficient application or database that can just push more and more and more data to the disk, either as a read request or write request, clearly at some point it won't gain you anything. There is a limit to the concurrency that the storage can support. And at some point, as demonstrated in this graph on the left, if you put too many requests at the same time to the storage, you just get higher and higher latency. So on Scylla, as you probably noticed, we do not like latency, and we want to manage our latencies ourselves and control them. So we want to use the storage in the exact amount of concurrency that bring the maximum efficiently, not less and not more. So first question, how to find this sweet spot in the storage. So first, it's not trivial. It's depend on many parameters, and the best way that we found is simply run a quick benchmark during Scylla setup, identified what is the sweet spot of the specific disk that you're using, and feeding that to the Systar platform. And from this point on, Systar will use this parameter to work with the disk. On some cases, like if you're using a cloud format, GCP, AWS, or Azure, we do know in advance what is the sweet spot of the disk used, for example, in I3 or I3N. So you don't have to run this quick benchmark. This quick benchmark, by the way, is part of Scylla setup, which is a small script that you run when you install Scylla and set up all relevant parameters in the kernel, measure the storage speed, etc. So implemented our own user space IO scheduler that takes requests, basically demonstrating the take request for from all the processes that the database run, both runtime requests, but also compaction, repair, and all kind of offline processes the database need to run. And we make sure to schedule all those resources ourselves. So we are not letting the kernel resources them based on OS priority, rather we take care of that ourselves. Earlier I mentioned that the IO scheduler, but we have similar scheduler for the CPU, networking, etc. So we take all of these tasks like commit log flash, compaction, query. Some of these terms might not be familiar to non-Scylla user. It just some of the processes that the database manages. The database is always more than online query. It's also have all kind of offline processes they need to run. And in Scylla, we make sure to schedule all of these resources ourselves. So that's bring me to the result part. So we redesigned the entire database. We rewrote it from scratch in C++. And this is the result we got. This is latest result that we got from comparing Scylla with Cassandra. We actually use both Apache Cassandra 3 and Apache Cassandra 4, which, by the way, are not the same. Cassandra 4 is better than Cassandra 3, but still the difference between both and Scylla is significant. What you can see in this diagram is comparing a cluster of 3 nodes from Cassandra and Scylla, pushing more and more throughput and testing the latency. So first of all, you can see that the throughput that you can push to Cassandra before it just breaks, it's relatively low. In this case, close to 10,000K or 20,000K for Cassandra 4, the latency start to jump and then the database simply overload and cannot function. Scylla can support a much higher throughput, but what I want to focus here is that even in this high number of throughput, the latency is very, very consistent and very, very low. And you can see here both the 90 and 99% latency. Both are super important, and we just, by the way, we did a full conference on that recently, on the P99 latency. But if your application is using multiple database query, this P99 is super important to you, and it's important to keep it low and consistent. By the way, if Scylla do detect a stall in one of the threads that increase latency, it will write an error to the log that you can monitor. So as far as I know, it's one of the, maybe the only database that write and increase latency as an error to the log, because we want to keep close track of latency issue. That's a similar, that was for read, this was for write. We executed many other benchmarks. This is just a sample, and you can search for the blog post that demonstrate the rest of it. One more comparison to Cassandra I want to show is we actually compare a 4-node cluster of Scylla with a 40-node cluster of Cassandra. And what you can see here is that while the throughput with a 10 times bigger cluster is relatively the same, the latency is still higher for many values. So many people say that you can fix throughput problem with money, just throw in more and more server, but latency problem, it's harder to fix, and just adding more nodes to the cluster won't fix your latency issue. And we also benchmark outscale and downscale. Let's keep that in the essence of time. And here is a concrete example from one of our customers that would actually able to reduce the number of nodes from Apache Cassandra when moving to Scylla while keeping the same workload. And that's, of course, translate automatically for saving cost on AWS, for example. So in summary, we quickly covered the change in hardware in the last 20 years, and we presented a novel database that used this kind of modern hardware to its advantage to create a database which have superior throughput and a low consistency latency. You can contact me at Twitter or my mail, and I will be happy to answer more questions. Thank you very much.